Okay, so today we are talking about the noble gas notation, and which is a little bit different than regular electron configurations, and it's a little bit easier, I think, as long as you have a periodic table handy. We're also going to talk about the D-block metals, and then we are also going to talk about some properties, some magnetic properties of electrons that have unpaired arrows or unpaired electrons in their little orbital boxes that we drew. So we're going to talk about what do we call those when they have unpaired and when they have paired up electrons. So like I said, this is lecture 3.5. The first thing we're going to talk about is noble gas notation. So noble gas notation is similar to the longhand notation, except I'm taking out what are called the core electrons. So the core, let me write that down, the core electrons are the inner electrons. So the inner electrons are basically all the numbers that come before the last one you put. Okay, so I'll show you that. So what Mr. Kahn told us is that the blocks on the periodic table are labeled. So remember, these two first blocks are the S block. These in between are the P block. Or sorry, those aren't the P block. Those are the D block. And these yellow ones over here are called the P block. So the P block metals, or the P block are mostly nonmetals. The D block are mostly metals, or actually they are all metals. The S block are all metals. These are the rare earth elements down here. Those are the F blocks down there. Okay, and then we also have, remember, our periodic table is labeled in rows. This is row 1, row 2, row 3, row 4, row 5, row 6, and row 7. Okay, so the easiest way to show you how to do noble gas notation is to do an example in longhand notation and then shorten it. Okay, so let's do phosphorus here. So I'll do phosphorus. Let me pick a different color. Go back to red, the standby. So remember, we start at the top of our periodic table here, and if I want to do for phosphorus, I want to get down to where I have 15 electrons, because it has an atomic number of 15. So I start at the beginning, 1s. Remember, that can hold 2 electrons, because remember that He should be all the way over here. For some reason, well, not for some reason, because it has the properties of a noble gas. They put it over there. So 1s2, and then I go on to, there's no more electrons in that row, so now I go to the 2s, and then 2s can fit 2. So that's a total of 4 electrons. Then I make my way over to the 2p. That's what comes next. Fill that up. That gives us 2p6. And then I go to the next energy level, which is 3. And I do fill a 3s with 2. And then the 3p with 1, 2, and 3. So I have 3p3. The reason I put 6 there is because I stopped where phosphorus. I didn't need to fill it with all the way with 6. So now I want to, that's my longhand notation, so that's the long hand. All right, so now I want to do the shorthand, or noble gas. So let me get the, change color here. Oh, purple. Okay, so now I want to just find out a way to show the last energy level electrons. Those are the ones that have the last big quantum number, which is 3 here in this case. Our principal quantum energy level. So I want to find a way just to show those, but I also want to show that I had the 1s2, the 2s2, and the 2p6 filled. Okay, so I want to use the noble gas that comes before phosphorus. All right, so the noble gas that comes before phosphorus would be neon. All right, and if you count up, neon has 10 electrons. Okay, so I'm picking that noble gas because I want it to take the place of my 1s2, 2s2, 2p6. And if I add up those superscripts, those exponents, that gives me 10, which is the same number as neon. So basically, you just use the noble gas that's before your element. So you always put that noble gas in brackets, and then you just simply write out your last energy level after that. Okay, so we kind of studied this last year, but you write out the one after that. So that's the noble gas configuration. Let's do another one here. Let's do the noble gas configuration of copper. Okay, so I could start at the beginning, 1s2, 2s2, 2p6, 3p6, 3s2, 3p6. I could do all that. Or I could start at the row I'm on. So 4. I'm on row 4, and the noble gas I would use would be argon. So I have argon in brackets. And then I have 4s2. And then I count over 1, 2, 3, 4, 5, 6, 7, 8, 9. So that would be 3d9. Remember that the D blocks are one level or one quantum number behind. So this starts at 3, and then the 4Fs are 2 behind. So I actually start at 4F instead of 6F where they should start. Okay, so that's a noble gas configuration. The next thing we need to talk about are our D-block metals. Now what makes those so special is they have certain properties. Sometimes when I have a half-filled energy level, okay, so if I look at an energy diagram here, I would fill up this in order here, remember, with our up and down arrows, 1s2, 2s2, and then I remember I would fill these up one at a time until they're all filled, and then I would go back and fill in the down arrows. So I would end with 2p6. Okay, so 3s2, 3p1, 2, 3, 4, 5, 6, and then I go up here, 4s2, 4s1, 4s2, there, 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 and the 3D. Alright, so let's look down here at our configuration table. Okay, so this is how these fill here. 4s1, 4s2, here's our D block here, what we're interested in. It goes 3s1, 3d1, 3d2, 3d3, 3d5, 3d5. So you would think this should be 3d4. However, it has a configuration of any element right there has 3d5, a configuration of that. Okay. Also over here, where you should think you would find 3d9, you actually find 3d10. Okay, that's because arrows, the 3d orbital wants to be filled, or half filled if it can be. Okay, so let's look at the configuration for chromium, all right, which is Cr. And Cr, let me check real quick, it should be, go back here, it should be that fourth element there. Okay, so we're looking at this one right here. So chromium. So I'll do the noble gas notation for that, which would make that Ar. And then I go 4s2, and then I should have 3d4. All right, but a funny thing happens when I have an element that has a half-filled d orbital. It is more stable than an element with only 4 electrons in there. Okay, so what am I talking about? So 3d has 5 spaces. Okay, so this is the 3d. And it would look like this to begin with, and then let me put the 4s here as well. Okay, so it looks like that to begin with. Okay, so it fills the 4s, 1, 2, up, arrow, so 3d4. Okay, however, this element is more stable if it promotes this electron to fill this empty space here. Okay, so it's more stable when it does that. Okay, so that's one of the kind of intricacies of this that you should kind of understand for the AP test. You have to basically know there's a couple exceptions. Chromium is one, copper is the other one. So let me show you copper here. So instead of writing 4s2, that should be 4s1, and this should be 3d5. So you just have to be careful about any elements here, for instance, chromium and copper. So let me show you copper here. Let me erase what we have here. Erase all ink on slide. Oh, I like that. Okay, so let's look at copper. Copper should be right here. All right, it has 29 electrons, so my noble gas would be argon, and then 4s2, and then I have 3D9. So that's what it should look like. So it should look like 4s2. That should be the 3D. So 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so it should look like that. Okay. However, to become more stable, it will promote that electron out of 4s. Okay, we'll promote this one out of the 4s, and it will fill that d orbital. Okay, so it's a lot more stable when those lower energy levels are full, and I just have one electron in that outer energy level, which is the 4. Okay, so be on the lookout for chromium and copper, because they actually copper should be 4s1, 3d10. Okay, and the very last thing we're going to talk about is the terms paramagnetism and diamagnetism. So paramagnetism are those species that are attracted by a magnet because when they are created, when you have unpaired electrons. So paramagnetic, let me write the definition here. So those are species, okay, are elements, which should say elements, attracted by a magnet, because it's dealing with by a magnet when it has unpaired electrons. Okay, so like this electron, so like this configuration, for example, it has an unpaired electron right here, which makes it attracted to a magnet. Okay, so that's the term paramagnet. Anytime I have unpaired electrons. So as you can guess, the term diamagnetic, those are repelled. Slightly repelled by magnet. That's because they have all paired electrons. Okay, so it's got paired up there, 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 and there. Okay, so it is repelled by a magnet. So those are the two terms you kind of have to deal with. If it asks you to write the configuration and then determine whether it is paramagnetic or diamagnetic, that's how you would figure out what they're talking about. Okay, so I hope you enjoyed your holiday and your long weekend, and I'll see you in class tomorrow.